Okay, now we will talk about um, changing variables to make the integrals easier. And we're going to use a transformation. And we'll call it t. And what it's going to do, it's going to allow us to go from one region, say R, to another region, S. And hopefully the second region is going to be easier to integrate over. That's the point. And we'll take this point UV, and the transformation takes it to xy. So t of UV is going to equal xy, where x is a function, where x and y are functions of u and v, and they have continuous with continuous first partial derivatives. Okay, then if t is 1 to 1, that means each point UV has only one image point, and each image point is paired with only one domain point, so they can go back and forth. So if t is 1 to 1, then remember the inverse of t exists. Now, in one dimensions, for an example, remember how we change the variables with substitution. If I wanted to integrate from 0 to 3 square root of x plus 1 dx, we let u be x plus 1. Then du was dx. We'll just take a really simple example. And our limits, since these were x's, changed to u's by substituting them in for u. This turned into the square root of u du, and now we can easily integrate. So that's the idea behind this. With double integrals, what we're going to do is take this region S and let's take the corner point u0, v0, and translate it over here to R. Let's say this is S, and this point is going to be x0, y0. That's the image point, and we'll say this is the vector R. So t of u0, v0 is x0, y0. Okay, we're going to let R be the position vector of the image point. So let me draw a bigger picture. Say this is my region R, and this is point u0, v0. So this is R u0, v0. We're going to let that be the point u0, v0 plus delta v. And we're going to let this point be u0 plus delta u, v0. Now, if So this is the vector r u0 plus delta u v0. So this vector right here in red, the red vector is r u0 plus delta u v0 minus r of u0 v0. And this one is r of u0 v0 plus delta v minus r of u0 v0. So we'll call this vector b, and we'll call this vector a. So this is a is in red, and b we'll say is blue. So a divided by delta u is approximately the partial of r with respect to u, because if we divide this red expression right here by delta u, that's the first partial with respect to u without the limit. And if we take b and divide it by delta v, then that's approximately the partial of r with respect to v. Now, the area of this parallelogram made by A and B, so the area of the parallelogram is approximately the area of R. Let's go back and look at the picture. If I take this parallelogram made by A and B, the area of that is approximately the area of our region. The area of this parallelogram is the magnitude of A cross B, which is RU cross RV delta U delta V, because A is approximately, we'll say, RU times delta U, and B is approximately RV times delta V. And RU cross RV is the determinant of this, because R is a function of X and Y. Okay, and this is called the Jacobian. So, and we'll say that's J. The area of R is approximately the Jacobian times delta U delta V. Now you're going to add all those up, just like with Riemann sums. We're going to add the image rectangles, means all the R's of S, and take their limit, and we get the double integral over S of x, f of x of u v, because x is a function of u and v, and y is a function of u and v, times the Jacobian du dv. And you can look at the example homework problems to see examples of how this is done.